Welcome to your topic on RedOx reactions. It is an internal. It is worth 3 credits. Okay, so I just want to link this back to the knowledge that you've already got. So last year in chemistry, you looked at different types of chemical reactions. One of them was precipitation. And we've extended that this year into identifying ions through precipitates. So we've got that. Next, you did last year what we call displacement reactions, where one metal is more reactive than another metal and displaces it in solution. So let's have a wee look at those displacement reactions. I'm going to put a couple up on the screen, and you'll probably recognise them. So let's just have a wee note about this. This links back to the displacement reactions you did last year. Okay, so that was involving metals, a more reactive metal with a less reactive metal ion. So remember we put the iron nail and copper sulfate. So let's put iron, I'll show you a tube of this in a minute. Iron nail in copper sulfate solution. Remember those displacement reactions were really a fight, or as Māori would say, a whawhai, between iron and copper. Remember, the sulfate was just a spectator. So this was a battle between two metals for supremacy. What do metals actually want? They want to lose electrons. So here's two metals that like to lose electrons. And the more reactive one says to the less reactive one, well, I want to lose electrons, so you're going to have to take them. So copper's forced to do what it doesn't want to do, it's to take its electrons back. Okay? That's what metals don't like doing, taking their electrons back. But because iron is more reactive than copper, iron gets to be the boss. So here's what happens in the reaction. We have iron, and that's just metal iron. It's not an iron. Oh, I hate that. Okay, that's iron, and we put it into copper sulfate. Copper 2 plus, sulfate 2 minus, so CuSO4, and that is in solution. And what we see is what colour would this be? Blue. Good. Copper ions. Fabulous. So we see the blue colour start to fade and another colour replaces it. The colour that replaces it is green. So what does that tell you? Yeah, we've made Fe2 plus anyway. So we already know the iron is giving away 2 electrons. It didn't make Fe3 plus, it's not going red. Okay? But what we find on the nail, you get the nail now has a red coating. What's that? Copper metal. Okay, so what we get out of it is FeSO4, and copper metal forms on the nail. It's not rust, it's not iron 3 plus, because that's why rust is red. It is copper. Okay, so we have to unpick what actually is going on. Now, first of all, we have to say, well, where's the spectator ion? Where's the ion that really hasn't changed what it's doing? Which one is the spectator ion in copper sulfate? Yeah, the sulfate. Okay, so I'm not going to worry about the sulfate. It's quite nice. It's quite liberating. Don't have to worry about the sulfate. So what's happened to the iron is the iron has become what? An iron. And what's its charge? Yeah, Fe2+. So we've seen that change. Okay, what did copper start out as?
An iron.
An iron. Okay, so we know copper is an iron here. So when you have a fight or a fight between two, one is going to start out as an atom and the other one is going to start out as an iron, and the atom is going to force the iron to take back its electrons. Okay? It's a fight between two metals. So copper became what? Yeah, it became an atom. It was forced to take back its electrons and it became an atom. So that's how we write it. So we've got to be really, 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 really careful with what we make an iron and what we make an atom, and really, really, really understand in our own brains the difference between an iron and an atom. They're two incredibly different things. And it's just the difference between a few electrons, but it makes all the difference. Okay, and that's why we're quite pedantic about charges on ions, as some people in the test will find out. Okay, so what has happened to the iron? I've got to make this side of the equation balance with this side. Nothing's changed in my equation. I've got to make the amount of matter on this side the same as the amount of matter on that side. What has this side got? Which one has got more matter, this side or this side? More stuff. This one? Yeah, it's got 2 electrons more, hasn't it? So I've got to add 2 electrons here to balance it. Is that balanced now? Iron can be split into the iron 2 plus iron and 2 electrons. Is that correct? Does that make sense? Well, yes, miss, but I've never done that before. Yeah, well you can. We can show electrons in equations. We don't show them in overall equations, but what you have to do is these little half equations to say what's actually happening. Alright, on this side, which side needs the electrons? Yeah. Okay, so let's unpick what we did. First of all, we identified the species of interest. And when we talk about what's happened to these 2 species. We're not saying what's happened to these 2 species, that's the result. So we're saying, well, what happened to iron in this equation or in this reaction? It was split into an iron and 2 electrons. What happened to copper 2 plus in this equation, in this reaction? Oh, it was forced to take back its electrons to become solid copper. And that forms on the iron. Forms on the iron metal because that's where the electrons are coming from. Okay. Do you notice that the electrons are the same on each side of the equation? That's important too. You can't have the electrons on the same side because that's like saying both are giving them away but no one's taking them. Can't have that. If you're trading electrons, someone's got to take them. You can't both give them away. Alright, so we identified the species of interest. In this case it was iron, solid. Oop. It was iron, solid and Cu2 plus Aq. Alright, who did we identify as the spectator ion? Sulfate. So we leave out the spectator ion. Because really, it's an iron here and it's an iron here. Oh, with the same charge. So it's not taken electrons, it's not given them away. So we leave out the spectator. then we write a half equation for each species of interest. Which shows the electrons. Alright, so we figure out from the first equation what went from being a metal to be an atom to being an ion, and what went from being an ion to being an atom. Okay, I'm going to get a bit creepy now. Alright, that sometimes happens in explanations, a little bit creepy. I'm going to sing a song. Okay, I'm going to sing a song. I want you to remember the song. And yes, you're filming it, and yes, it is going to be a private station. Okay. It's an old song, but a good song. Love and marriage, love and marriage goes together like a horse and carriage. Love, forgotten the words now. You can't have one, you can't have one, you can't have one without the other. Alright, this is like RedOx as well. RedOx stands for reduction and oxidation. Now, there's ways of describing reduction and oxidation, but oxidation is when something gets oxygen. Sometimes. That's the way you can say you had magnesium on this side of the equation and magnesium on that side, magnesium oxide on this side of the equation. We'll do that equation. Magnesium's definitely been oxidised because it's got some oxygen that it didn't have before. So that's one way, but there's no oxygen in here. So there's another way of identifying oxidation. Okay, I'm going to write, what do you associate when you hear the word Leo?
Lion.
This is the creepy bit. You thought the song was the creepy bit. Nah, this is the creepy bit.
Lion.
Grrr. Grrr. Okay. Yeah, it's creepy. Grrr. Okay. Leo, the friendly lion, roars grrr. Yeah. Leo, the friendly lion, he's not that friendly actually because he's roaring. He roars grrr. Now, that's to help you remember. Remember, gaining oxygen is oxidation. Also, losing electrons is oxidation. Ooh. Lose electrons. Lose is only one O, isn't it?
Yeah.
And choose is two. Oh, I love this language. It's so logical. Not. Electrons, sorry. Now I'm completely mucking up. Electrons. Oxidation. Because we also have to identify what's been oxidised and what's been reduced. Okay. What do you think this stands for now? Gain electrons of reduction. So gain electrons oxidation.
Reduction.
Reduction, that's what I said. You're just trying to confuse me now. Right, okay. Now I've stumbled through that. So I have to say, well, where has oxidation happened and where has reduction happened? So Leo tells me loss of electrons is oxidation. So I need to look at something that's lost electrons. Okay, iron went from being an iron atom and it lost 2 electrons. Egads. Lost electrons, oxidation. So I just put in O. That's been the oxidation reaction. Cool bananas. Okay, because we know that metals like to lose electrons. They like to be oxidized. They want to be oxidized. They need to be oxidized. They dream of being oxidized. Okay, but poor old copper's got the raw end of the deal. Copper doesn't want to be oxidized, but it has reduced, but it hasn't got no choice. When you put an O on one equation, you figure out who's being oxidized. This is where the song comes in. You can't have one. You can't have one without the
Other.
You can't have one. You can't have one. You can't have one without the
Other.
Getting there. Try one more time. You can't have one. You can't have one. You can't have one without the
Other.
Yeah, okay. Don't give up your day job. Alright. So I automatically know that the other equation is a reduction equation. I can't have 2 oxidation equations. Okay? Because you've got to have one with the other. And here's why. For someone to take electrons or get given electrons, they've got to come from somewhere. We don't just magic them up. So they're coming from the iron. So when you do 2 half equations, you've got to make sure your electrons are on opposite sides. If your electrons are on the same side, warning, Will Robinson, warning. Does everyone know what that means? Oh, we need a YouTube clip on that one too, CJ. I'll get the YouTube clips up in a moment. Okay? Warning, Will Robinson, warning. Danger approaching. All right, I'll show you that. I think there is a YouTube clip. Okay, it's the Lost in Space robot that does that. Okay, but I can't wait to show it to you now, but never mind. We'll just finish this. All right, so I've got to write a full equation out of these 2 half equations. Now I've figured out what's been oxidized, what's been reduced, and basically I've got to write the full equation without the spectators. And I know how some of you love those spectator ions and try to put them in all the time, but you must stop it. Okay, so if something is on this side and something is on this side, I can cancel it out. So what's on this side that's also on this side? The electrons. So they're gone. They're sorted. So I just have to write an equation. And this is how I do it, because it gets a wee bit more complicated than this. This is an easy one. Okay, so I write Fe solid, cross them out, I've written it, plus Cu2 plus Aq, cross him out, don't use him again. Now I don't put I just put RedOx like that, okay, because it's oxidation and reduction now because I'm combining the equations. Fe2 plus Aq plus Cu solid. And I cross them out, and as I cross them out, I'm checking I've got exactly the same thing. I haven't stuck 2 plus on here by mistake or anything like that. So I do a visual check. Oh, didn't need to cross that one out. Just a bit carried away. There we go, you can stay. I'll just fix you up. There we go. Touch you up a wee bit. Okay, and that's my full equation. And I get excellence.